section 5.4, modeling and optimization. And if you look at the what will we learn about section, examples from mathematics, examples from business, examples from economics, modeling discrete phenomena with differentiable equated functions. Basically, this is the core base of calculus. Calculus was first created and used to optimize things. That's what I said at the start of this chapter. We want to maximize profit or minimize cost, things like that, and we can use calculus to get us there. So now we're looking at all different types of application problems and using our analytical skills, first derivative test, second derivative test, totality test, things like that, to find when the maximum or the minimum that we are looking for will occur. All right, so strategies for solving max-min problems. This is what they have in the book. And I thought we'd just run through and look at these. It's essentially how we approach a word problem. Okay? Understand the problem, so you need to read it carefully. Develop a mathematical model of the problem. So, drawing pictures, labeling parts. I always want to write down what I want to know and what I do know. Things that are given and exactly what I'm looking for. Graph the function if you can. Find the domain of the function. Then we'll be identifying critical points and then finding maxes and mins. Now, the only thing I would add to this little list, so after they have identified critical points and endpoints, solve the mathematical model, that's where we're going to use our analytical skills from calculus to find our maxes and mins, and then interpret the solution for the problem. The only thing that I would add in is when we develop our mathematical model, number 2, you should be aware that you may need a primary equation and a secondary equation. Okay? A primary equation is the one we're trying to maximize or minimize. That's what you should always be clear about. The primary equation is the one that we're trying to find the max or min for. The secondary equation is usually there to help us get the primary equation in terms of one variable. Just like when we had systems of equations. We would have the second equation, we could solve for one variable in that and plug into the first equation. Same idea, so that we're in one variable, so that when we take the derivative, there's only one variable that we're dealing with. Okay? So, other than that, we just need to try some problems. There's 2 from the book that I pulled, and then there's 3 on your packet that you're going to get today. So, example 1 says, find 2 numbers whose sum is 20 and whose product is as large as possible. So what are we maximizing? The product. We are maximizing the product. Okay. And the sum of, find 2 numbers whose sum is 20. How can I write that? What kind of model can I write for that, Calvin?
X plus y equals 20.
X plus y equals 20. And whose product is as large as possible. So I'm going to say M equals, that's the maximum product, equals what times what? Y. All right, so here you can see this is our primary equation. This is our secondary equation. Secondary equation is here only to help us get the primary equation in one variable. So what can I do with the secondary equation? Solve for what?
One variable.
Yeah. So let's solve for y equals 20 minus x. And we can say m equals x times 20 minus x. And I want to find that maximum of the product. So what do I do? How do we find a maximum? How do we find where the maximums occur? Find where the derivative equals 0 or is undefined. We find our derivative. Probably easiest to make this 20x minus x squared to take the derivative. So m prime would be, little louder?
20 minus 2x.
Thank you. That is defined everywhere, so there's no place it is undefined. All right, so we find where that equals 0. X equals 10. I have only found one critical number, but we cannot assume that that is a maximum. You do have to check to see that it is a maximum. So we need to oh yeah. Sorry, there. All right, so we need to check to see if it's a maximum. And how can I do that? Look to the left or right. We could do the first derivative test, right? We could do the second derivative test. So I'll just set up for the first derivative test. All right, so our critical point is 10, and if we look negative infinity to 10, and 10 to infinity, we pick a nice test value. What's a nice one here? And here? 11, sure. We look at f prime of the test value, and if I put 0 into my f prime, m prime in this case, what do I get, positive or negative? I get a positive. Come back. And if I put 11 in, I get a negative. Increasing, then decreasing means I have a maximum. Now, do remember with these max and min problems, if it says to justify your answer, what we have done here is not enough. You would have to include a sentence that says, we get a maximum product at x equals 10 because the derivative of the product changes from positive to negative at x equals 10. Okay? All right. Questions on that one? That's a classic basic starting problem for optimization problem.
You plugged the first derivative, right?
Yes. Yep. Since we're using the first derivative test, we plugged into the first derivative. Okay? Questions on what we did here? All right, one more, and then you're working at your desk. This is a classic also, both of the examples that they have here are very common types of problems. Sorry. Acting real funny. The problem says a rectangle is to be inscribed under one arch of the sine curve. Okay. I can make it bigger over here. Okay. A rectangle is to be inscribed under one arch of the sine curve. What is the largest area the rectangle can have, and what dimensions is that area? All right, right now, draw yourself a picture. One arch of the sine curve. You're going to have a rectangle inscribed in it. So we could think of it, oh boy. Like this, and we've got some rectangle inscribed in there. I found it easier to actually shift my sine curve to the left by pi half. So remember, this is 0, this is pi half, and this is pi. So if I think about shifting this to the left pi half, I'm doing it between negative pi halves and pi halves. Cool, there it is. And my rectangle is coming in here like this somehow. And the reason I chose to look at it this way is because that rectangle is going to be centered underneath this arch, and it made it easy for me to see that I could call this distance x. Yeah, Calvin.
I like the pool.
Go ahead. Yeah, go ahead. All right. So it just made it easier to see that the rectangle, I could call half the rectangle x. So the dimensions of the rectangle are easier for me to define. So the rectangle could be defined by what equation? The area of the rectangle, I should say. Idea. So my width will be what? 2x. What about my height? Height will be what? F of x, which is? What's the function? Well, it's sine, but we need to think about what we did with that equation. So this is y equals sine of x. And I shifted it pi halves to the left. So what is the equation for this function? We could call it cosine, sure. Yep. Or we could do it with a shift on sine. Sine of x, then what? Plus pi half, because inside it's always opposite of what we would expect. Or we could call it cosine x. Either one would be fine. Okay? So, keeping it in sine, we would have 2x times sine of x plus pi half. Like that. And we want to do what with the area? Maximize or minimize? Trying to find the largest area. So right now, all of you find the largest area. Maximize that area. Find where the maximum area occurs. It would be good if some did it with cosine x, some did it with sine of pi, or x plus pi half. Let's see it both ways. Okay. So working on the solution up here. All right. So if you look up here, I have my solution. We look at a prime. We do the product rule, first times derivative of the second, plus the second times the derivative of the first. And look to see if that is defined everywhere, and it is. They are just sine and cosine functions, which are defined everywhere. So we now need to find where that derivative equals 0. I factored out a 2, and we get 2 equals 0 as one of our factors, which gives us nothing. And then we get x cosine x plus pi half plus sine of x plus pi half equals 0. We're going to solve for that x, and And what I end up doing is getting x equal to negative sine over cosine of x plus pi half, which is negative tangent, and at this point we would need our calculator. The easy way to solve it is put x in y1 and the negative tangent expression in y2. Does anyone have a solution? Jake, you have one? No? Anyone get there? Okay, get there now. The intersection is where? And this is you have it? 0.5 something? So for our x, oh yeah, 0.86. Yeah. Yep. I'm remembering a different problem, I think. So we get x equals 0.860. All right, well, what if I asked, and I think it was part of the question, the dimensions of the rectangle would be what? How would we find it? The width would be what? This is the x value we found. So it's 2 times that, right? So the width would be 2 times 0.860, which is what? 1.72. And what about the height? How would we get the height? Plug it into that sine curve. So we've got sine of 0.860 plus pi half. Whatever that comes out to be. Someone have that for me? What is it, Bridget? 0.652 sounds familiar. And then what is the maximum area? All of these things you would be asked to find after your analysis. So what would the maximum area be? This times this. Jackson, can you press that in for me? 1.72 times 0.565. 1.12, thank you. Unit squared. And we've answered everything we need to. Yes, no.
When you put the equations in the calculator and you were trying to solve for x, when I put in negative 10, it intersects everywhere with y equals x. So how do you know what the x value is?
We are interested in that first arch of the sine curve, right?
Oh, okay.
So you want to be in that area, okay? All right, anything else on this one? Okay, so in front of you, you have a packet, and what I would like you to try and finish in class are the 3 problems on the front page. Consider this part of your homework as you need to. Then the rest of this packet is just for you. You can never have enough optimization practice problems. They can come from every genre. They can come from geometry, they can come from physics, they can come from business. So you need lots of practice. Okay, I won't be checking this packet except for the front 3. Otherwise, it's just for you, and you can come see me if you have trouble with any or you want to check any answers. Okay? So right now you're working on the front 3. What's that? Yeah.